Imagine a world with three types of numbers. How would we even start? Think about this for a bit, and then continue forward. Meet the world of perfect numbers, where every number falls into one of three qualities: deficient, abundant, and perfect. In this video, I will explain to you what these terms even mean, tell you many amazing facts about these numbers, along with some other tidbits. Let's get started. To tell which category any natural number that falls in, use this algorithm. First, find all of the positive numbers that divide it besides itself. Then add all of them up and see what you get. So let's have three examples to make sure you understand. Let's try with 9. The divisors of 9 are 1 and 3. They add to 4. 4 is less than 9, so it's deficient. So to summarize, if the sum of the divisors of a number is less than that number, it is deficient. If we try it with 12, however, you can figure out that the divisors are 1, 2, 3, 4, and 6, which add to 16. 16 is more than 12, so it is abundant. And finally, let's try 6. The divisors of 6 are 1, 2, and 3, which coincidentally add up to 6. That makes it perfect because the sum of its proper divisors equals the number itself. For fun, you can try to find the next perfect number. For a hint, it's less than 50. This may seem like all there is to these numbers, but there is more. For history and some fun facts, continue watching. By the way, the answer to the next number, is 28. First, let's start with a brief history. The perfect numbers have actually existed for a pretty long time. The Pythagoreans studied perfect numbers in roughly 500 BCE, but they only knew about the first two, 6 and 28. They described them as symbols of health, beauty, and marriage. Next, we move on 200 years later to Euclid. He proved the first mathematical result of these numbers. Basically, if 2 to the power of p minus 1 is prime, then 2 to the power of p minus 1 times 2 to the power of p minus 1, which doesn't make any sense, but it does, is a perfect number. This formula found the first 4 perfect numbers: 6, 28, 496, and 8,128. Of course, mathematicians seem to enjoy proving things, so let me give you a proof for why this is true. So you don't have to go backwards in the video, we're trying to prove this statement. Our definition for a perfect number is that the sum of its divisors must add up to itself. That means that if we include itself, then the sum would be twice as large. For example, the sum of the divisors of 6, including 6, would be 12. That's our first step. Next, we try to come up with a formula for the sum of the divisors of our particular number. Let's try 45. Well, any divisor has to first have some amount of powers of 3, right? It can't have a power of 2 since 45 doesn't have a power of 2. 45 has 2 factors of 3 because it divides 9. So our divisor can have anything between 0 and 2 factors. It can't have more than 2 because 45 doesn't divide 27, which is 3 to the power of 3. So it wouldn't be a divisor. The same thing goes for 5. It can either have 0 or 1 factor. So if we use the distributive property, we can write that the sum of the divisors of 45 would be this. This includes every possible divisors because there can be any number of 3's, so 0 3's, 1 3, or 2 3's, and any number of 5's, 0 5's, and 1 5. So now we can use this for a proof. So we're assuming that 2 to the power of p minus 1 is a prime. As said earlier, if this is a prime, our number is that multiplied by 2 to the power of, in parentheses, p minus 1, which is a power of 2. So in writing the sum of the divisors, we get this. First, we either have 0 powers of 2 to the p minus 1 or 1. And the amount of powers 2, well, we can have 0 or 1 or 2 or 3, all the way up to p minus 1. And the left side cancels to make 2 to the p, and the right makes 2 to the p minus 1. Wait, but why is that? Well, suppose we were to add 1, or 2 to the 0. Well, these first two would add to 2 to the 1. And those would add to 2 to the 2, and so on, until we get 2 to the p. But since we added 1 in the first place, we have to subtract 1 to get 2 to the p minus 1. Wait a second. 2 to the p times 2 to the p minus 1 is exactly twice the number. So if we subtract the number from itself, they are the same. Therefore, this formula does give perfect numbers. No worries if you didn't understand that. Just note that we can check that this formula works. If we plug in p equals 2, which makes 2 to the power of p minus 1, a prime, or 3, we get 6. Lo and behold, that's the first perfect number. However, though this was published in 300 BCE, the next perfect number is found nearly 1500 years later. We're going to skip ahead a bit to the 18th century with the star Leonhard Euler, who proved so much math things, including one about pi in the harmonic series, but we won't go into that. So, in 1747, he proved the converse of Euclid's formula, or that all even perfect numbers follow that pattern. And what we mean by that is any even perfect number must be written as the form this, 2 to the p minus 1 times 2 to the p minus 1. We won't go into that, it's advanced. Soon, with the rise of computers, the search began. We currently know 52 perfect numbers. But you're not going to go looking for them yourself, because these numbers grow fast. The last one has 82,048,640 digits. Yes, you read that right. 82 million. That's a lot of digits. There are still many unsolved problems about these numbers. The main one is, are they all even? However, there are a few other significant ones, including, are there infinitely many perfect numbers? But okay, I think that's enough of these numbers. I think you've gotten slightly bored. So let's move on to a different topic. Take the number 220, find its divisors besides itself, and add them up. Well, we don't get 220, so it's not perfect, but we get 284. So what's special about that? Well, if you add up the proper divisors of 284, which are just the divisors besides itself, you get 220. So they actually go to each other. They form a chain. These numbers are known as friendly or amicable numbers. This is the smallest known pair. The Greeks referred to them as a symbol of perfect friendship. Since I'm weird, I'm not really going to go too deep into the history of these numbers. However, I do want to mention this. In 1866, a 16-year-old Italian boy, Niccolo Pagani, discovered the pair 1,184 and 1,210. This pair is the second smallest in existence, yet had been overlooked by every professional mathematician for over 2,000 years. Time for some facts and questions. First, over 1.2 billion, that's a lot more than 52, of these pairs have been found, but major questions remain. For instance, are there infinitely many of these pairs, or will they be the same parity? And parity means basically whether a number is even or odd. So basically, will even number always be paired with an even number and an odd with an odd? And also, do they all share at least one common factor? Because all of them share at least one factor, like 220 and 284. They share two, and so do these. None of these questions have been answered. One final thing before we finish. These are sequences known as sociable or aliquot sequences. This means that they repeat after 3 or more numbers. Here are a few facts. Currently, mathematicians have found cycles of 4, 5, 6, 8, and 28, which is weird, but not 3. But I must admit, the 28 cycle is really one of a kind. There is also something known as the 276 mystery, and basically people don't know whether it goes on to infinity or converges to 0. But wait, you ask, why would a number get to 0? Well, most numbers go to prime. Primes go to 1 because they have no divisors besides themselves and 1. And 1 goes to 0 because their only divisor is 1, but we can't have itself. So we get 0. There are so many more fascinating things I could say on this topic, but I think our journey has come to an end. If you learned something while watching this video, please remember to like and subscribe. Now see you in the next one.